Welcome, everyone. First, a couple of announcements. Your homework 3 is due tonight only, so tonight at midnight. If you forgot to do it over the long weekend, you still have some time. And project 2, multi-agent Pac-Man, is due on Friday at 5 p.m. Homework 4, MDPs, is going out tomorrow. We have 4 lectures on MDPs. The homework that goes out tomorrow will cover today's lecture and last week's lecture. So once it goes out, you're able to work on it. And it'll actually be quite useful to work on it soon so you can understand the next 2 lectures. It'll be due Monday at midnight, usual date and time for homework. Midterm dates and times have been finalized. They are on the slide here. There is March 12th, 5 to 7 p.m. This isn't, I think it's a Tuesday. Instead of lecture, we'll have midterm, but it'll be a half an hour longer than lecture. It'll be 2 hours. And same there in April. Also, it's also a normal lecture slot, but extended by half an hour. And with more specifics forthcoming, we'll actually split over 2 rooms because we have too many people to do midterm in 1 room. Any questions about logistics? Okay, then let's start with our second lecture on MDPs. And let's recap things a little bit here. One thing that's definitely happening in this course is that since last lecture, we've shifted gears. We've gone from a very algorithmic course to a more mathematical course. And that's just the way AI is these days. There's a lot of math, and we're going to be doing a lot of math, a lot of equations rather than just algorithms. So let's recap our running example. Our running example is a maze-like grid world with an agent who lives in the grid. This is a 3x4 grid. This square here cannot be accessed. It's a big wall. Then over here is the fire pit. You don't want to end up there. Over here is your ideal outcome, the diamond. That's where you want to be. When an agent moves, the agent doesn't get to choose where they go deterministically. You choose an action. You have 4 actions available in every of the normal states. If you choose the action north, for example, 80% of the time you'll succeed and you'll move north. But 10% of the time you'll instead move east, and 10% of the time you'll move west. If your action leads into a wall, you'll just stay put. So that's the big difference now, is that things are stochastic. You don't know what the outcome of the action is going to be. Then there are rewards. Rather than just having a utility at the end of the game, every time step, there is a reward associated with what just happened. You have a state, current state, an action, and then a next state. For that triple, there will be a reward associated with it. In our running example, often the reward function is some small negative value for any triple pretty much, except for if you happen to be in this state over here, you take the exit action, then you get +1. And in this state over here, you take the exit action, you get -1. But in general, this could be any 3-dimensional table with numbers, could be your reward function, with an entry for every state, action, state, triple. The goal is maximize the sum of discounted rewards. And we actually can't do that directly. Just like in Expect-to-Max, where you can't directly optimize the outcome you're going to get, the best you can do is optimize your expected sum of discounted rewards. And that's what we're after here. So the way we drew this out, and there's a very close connection to the Expect-to-Max trees, is to say there's a Markov decision process. It has states, it has actions. That's the same as in Expect-to-Max. We now explicitly model transitions in a transition model. And the probability to go into state S prime if you started in state S and took action A is given by this expression over here, or also this expression over here. That's a transition model. 2 ways of writing the same thing. Transition models are also 3-dimensional tables with numbers all between 0 and 1. The reward function is a 3-dimensional table over state, action, state triples, telling you how good a particular transition was. And often we discount. Remember, the reason we discounted, there were 2 reasons. One reason is rewards that come later in the future are less desirable than rewards that come now. That's often the case in the real world, and by discounting we can capture that. If you think of money, that's the most direct equivalent here. If you had money now, you could put it in the bank, earn interest on it. If you only got it later, you lost that period of earning interest. That's what this gamma is capturing, the discount factor. Another reason to discount is just mathematical convenience. If you don't discount, then you might have to deal with state action sequences that now are infinitely long for us, such that the rewards add up to infinity. It's really hard to deal with different infinities and to say which one of these infinities is better than the other one. And so to avoid infinities, we say we discount. And because the infinite summation, gamma plus gamma squared plus gamma to the third plus gamma to the fourth and so forth, sums to a finite number, we know that the sum of all rewards, if we discount them, will be a finite number, and we can compare them more easily. And the quantities we were interested in were a policy. That's really the final thing we're after. And it says for every state, here's the action to take. So it's a table, a hash map for every state mapping to actions. For every state, there is just one action that your policy encodes. Utilities is sum of discounted rewards. That's what you end up getting. As we said, you're not guaranteed to get any particular sequence because this is all stochastic. So what we'll work with is something called values, and that's the expected future discounted sum of rewards. Values are associated with states. So with a state S here, you have a value associated with it, and the optimal value is the value that you get from that state if you were to act optimally from then onwards. What does that mean? It's not anything you're going to get. It's on expectation, on the average, if many times you got to start from that state, and every of these many times you did the right thing, the optimal thing, on the average, what you would get as your sum of discounted rewards is the value of that state. After you take an action, you land in what in expected max was a chance node. From that chance node, you're in a holding pattern in some sense. You already committed to an action, but you don't know yet what the next state is. So you're sitting there waiting for a stochastic transition that puts you in your next state as prime. These are Q states. For Q states, we have values too. And here the values are Q, SA, depends on both the state and the action you just committed to. And the meaning of those values is that if you were to act optimally from then onwards, what on the average would you be getting as your sum of discounted rewards? So the difference is here that you already committed to the first action, and from then onwards will be optimal. Okay, so those are our quantities. Then we said there are optimal versions of these quantities. V star, and in general star for us will denote the optimal thing. V star is the expected utility starting in S and acting optimally. Q star is the expected utility starting out having taken action A from state S already and then acting optimally. And the optimal policy, pi star, is the one that for every state prescribes what the optimal action is. Okay, let's take a look at what this looks like in our grid world. So we have all these quantities. What do the values look like, the optimal values? These are numbers, one number for each state. These values are always vectors, one entry for each state. What do we have? One over here. Does that make sense as the optimal expected sum of discounted rewards for that state? Yes. In that state, there's only one action available to you. It's the exit action. It'll give you a reward of 1, which means, yes, the optimal expected sum of discounted rewards is exactly 1. That's what you're going to get. Similarly here, -1. Let's look at some other positions. What's happening over here? 0.85. What does that mean? It means if you were to do the optimal thing from that point onwards, you will get an expected sum of discounted rewards of 0.85. Why not 1? Well, we do discounting, and you're not going to get the 1 right away, right? If you were to move over here, you'll only get the 1 at the next time step, so it's discounted. Then it's also the case that you don't always succeed. You might end up, instead of moving there, you might move up or down. If you move up, you stay in place. If you move down, you land in this not so great square. And then from that onwards, you'll be acting optimally, and you'll get the value that's encoded by those states. So in general, it's tricky to just read off what these values will be, but 0.85 is something meaningful. It's less than 1, and That's one is the best you could hope for here, and you do discounting. Maybe you have a living reward that's negative, that's also decreasing how much you get. Same here, 0.74, less than 0.85 makes sense because the right thing to do here would be to move there and then there. If you're lucky, these actions work out, you get 1, but discounted. And so forth. Here you get even less, less, and less, and even less here. So that's a pattern that seems right. Whether those are the exact right numbers, you can't just spot like that. You need to do a computation. But they look meaningful. Okay. Let's look at the Q values. These are Q star values. Q values is a two-dimensional table, an entry for each state and action pair. So we can still draw this on this grid world. We just now have 4 numbers on each state. Let's look at this one over here. Why is there only 1 here? There's only 1 action available, the exit action. So that's just 1 value for the exit action. Q star is the same as V star. Over here, the highest one is 0.85. Means that you try to move over there. That's the same as what we had here. In general, for all of these, the highest value for Q star for a given state is exactly the same as V star for that state. Right? Because V star assumes you act optimally. Q star is already committed to the action. If you're committed to the right action, then you'll have the same value as if you were to start from the state and act optimally. What happens over here is the most interesting state in many ways. The highest one is over here, so you'd like to move up. Now, there's an action here to move sideways. The value there is minus 0.6. What does that mean? It means that, why is this not minus 0.85, equivalent to what you have over here? Why is there a discrepancy between these two? They both seem to go into a 1 and then a minus 1 state. Okay, what's the difference? The difference is that this one here is 0.85 because if you succeed, sure, you get 1 at the next time. It'll get discounted. If you don't succeed and you stay in this, you instead move up, which means staying here, you'll try again and again for the 1. And so at the first time, the same thing will happen. You might or might not land in that exit state. But over here, if you fail and you end up moving up or down, you actually don't continue trying to get in here. This Q star value says that if I act optimally, after having taken this east action, which is obviously not the right action, what's my expected discounted sum of rewards? So the reason this is not minus 0.85 is because after you take that action once, you don't keep taking it. The Q star value is for acting east once and then onwards always doing the optimal thing. So that's why this is minus 0.6, which is not the same as 0.85. Okay. Now, something we saw at the end of last lecture is called the Bellman Equations. What are they about? They're essentially summarizing our principles of optimality in a very simple way. Bellman Equations say, to act optimal, step 1, take the correct first action. Step 2, continue to be optimal. Think about it. This is exactly what we write down in equations. So, what did we do? We said, we'll start at a state, we'll get to choose from a bunch of actions, and then we'll land in a new state S prime. And the way we defined our optimal value function was by looking 1 step ahead, just like is being said here. Just look at the first action, make sure you do the right thing, and from then onwards, you kind of define it as a function of itself. You say it recurs and continue to be optimal. So what do we have here? We say V star, the optimal value function, means you take the optimal action, the optimal thing. You have several actions here, maybe action 1, 2, 3, and 4 is action 2. That's the optimal one. That's the one you want. Q star itself, you don't get to choose in the Q state. It's stochastic. You have an averaging over possible outcomes. Just like in expect to max, you average over the possible outcomes to know the value of that chance node. What you average now is not a utility from the bottom of the tree. What you average now is the reward you're going to get for that specific transition. This reward that's happening right there on that transition, it's happening right there, plus what you expect to get in the future if you were to do the right thing from then onwards. What do you expect to get in the future? Well, we don't really know how to compute it per se with this definition here, but we know that by definition that's what V star is. V star is the best you can get from then onwards from a particular state. So this is averaging reward now and future. The future has a gamma here. Why? Because we discount. Often you do a substitution here to write this as one equation. This is the Bellman equation. This is Bellman's principle over here. It's saying the optimal value from a certain state is obtained by looking at what happens when you act optimally as your first thing to do. And then, assuming you act optimally, what do you get for that action? Well, for a given action, what you get is an average over all possible successor states of what you would get for going to that state. What you get for going to that state consists of a reward that you get right now and what you expect to get in the future. Okay, so these equations characterize V star. What is V star? V star is a vector with an entry for each state. So in principle, what you could do is you could take these equations. How many of these equations are there? If you have, let's say, 100 states, there will be 100 of these equations. You could take these 100 equations, which has 100 different variables appearing in it. It's a nonlinear system of equations. You could say, solve this system of equations. Some nonlinear solver solves it for you. And there you are. There's your V star. That's an option that you have. It's not the option we pursue, because it's a complicated set of equations to solve. It's nonlinear. But that's one option, to just feed it into a black box nonlinear equation solver, and there comes out your V star. 100 equations, 100 unknowns, just nonlinear equations, so a little tricky. Okay, what we said is, well, rather than going to a black box nonlinear solver, we're going to find out ourselves how we can solve this 100 equations. Okay, how do we do it? Well, we say, this characterizes the optimal values, and we're going to now decompose this. It's characterizing the optimal values in terms of themselves. It looks like a recursion. Why not really think of it as a recursion? And we use this as update equations rather than as a set of equations that need to be satisfied. And the way we justified that was by saying that at time 0, the optimal value, when there's 0 time steps left, is 0, because there's nothing happening anymore. And assuming that you know the optimal value for k time steps left, which we called vk, which is a vector with an entry for every state, we can, with this equation here, compute the optimal value for k plus 1 time steps left. What is this saying? It's saying that to know the optimal value for k plus 1 time steps left from state S, you need to consider all actions. That's expect-to-max, just an expect-to-max computation. Then, for each action, you need to compute an average because you land in a chance node. That's this type of average over here, just expect-to-max. And then what you average is current reward plus future expected rewards, and then you discount. So we took exactly this equation over here, but turned it into a recursion rather than thinking of it as a fixed set of equations. And by turning it into this recursion, we also gave it some meaning. Each of these values, vk, is a very particular meaning. If you were to not act infinitely long, but only for k time steps, what you really want to know is vk, not v star. So in addition to being able to solve for v star, we have an additional tool for when the agent only acts a finite number of time steps. We can find the value, the optimal values for that too. Okay, so this is just one way, keep in mind, it's just one way of solving for v star. We saw a method to solve for v star by running this, and we also showed that if you run this for k going to infinity, infinitely many times, updating this, this will converge. Why was this going to converge? We said that the difference between vk and vk plus 1 is just in that very last time step. The reward you get in the last time step is what makes it different. But since the reward in the last time step is discounted by gamma to the power k, that means that if k is large enough, that's negligible compared to everything else. And so at some point, that difference becomes essentially 0, and that's when you have convergence. Okay, Any questions about this? All right. So that was a recap of things we looked at last time. Question there. Okay. So what does K mean here? What K means here is how many time steps that are left. So K is an index, and it refers to time, but in a backwards way. It's how many time steps are left or ahead of the agent before things are over. Okay, so we know now we can recap value iteration, value functions, and so forth. Let's look at something else now. What we'll look at now is policy methods. What's the idea here is that we come in with a policy, and here you have two robots come in with a policy, our smart and our not so smart robot. Both have a proposal policy for this grid world. That's our running example. We look at it, one of them is better than the other, right? But we haven't really seen how to formally evaluate this. If you're presented with these policies, how do you compute how good they are? So that's called policy evaluation. How is that different from what we've done so far? Well, the difference is that the policy is fixed. So rather than thinking of this expected max tree, and this is actually one very high-level thing for this lecture is that we're always referring back to expected max. And you might think, well, why weren't we done with expected max? Why is there still this lecture that runs value iteration instead? There are two reasons. One reason is that expected max has trouble with infinitely deep trees, and we're dealing with agents that are going to act infinitely long here, so computationally becomes a little impractical. Second, expected max doesn't exploit the fact that there would be many, many repeated states in that infinitely deep tree. And methods like value iteration make sure to compute things only once rather than do repeated computation for trees that are essentially the same subtrees. So value iteration you have to think of as a more efficient way of solving the same problems expected max could solve, but for the problems we'll look at, more efficient, often much more efficient, and we'll be able to build learning on top of it later in the next two lectures. But the intuition is still the expected max intuition. You can always think back to that expected max tree. That's where things are really embedded into. So what do you have? Standard expected max, choice of actions, and then some chance node. With fixed policies, what that means is that instead of a choice over actions, you have a fixed action prescribed by your policy for a given state. You're in state S, the action you're going to take is pi S. So you still have an expected max tree, just at the maximizer node, there are no options. Just one option. You have no choice. That's what you're supposed to take. You can still compute an expected max value. It's not any harder to do. In fact, it's easier to do. It's more efficient because somebody already fixed the choices for you, so the tree actually doesn't have as much branching. If you were to do that, if you were to run expected max in this kind of tree, what you get out is the value of that fixed policy. Might not be a good policy, but you would get out the value of the policy. So if these two robots came to you with their policies, you could build the according expected max trees. They're a little deep for you. They're infinitely deep, but let's assume you can handle that. Then you could run expected max in the two trees that you get, one for each policy, see what the values that you get at the top, and that will tell you the value of each of these policies and you can compare. Okay. So what we're interested in now is to turn that into a value iteration-like algorithm rather than expected max, so we can be a little more efficient. We'll now have something called V pi. V pi is the value for a state, assuming you fix the policy pi. Compare this to V star. V star was assuming you did the optimal thing. From then onwards, V pi is assuming you always use the policy pi, which is some table that maps states to actions. Then we can define it in the same way we did for V star, recursively, with a one-step look-ahead equation. What is this saying? Let's break it down. The value, which is the expected sum of rewards in a discounted way, starting from state S, acting according to the policy pi, is equal to our max is gone. Why is our max gone? Well, the first thing we do is still take an action, but the action is fixed. It's the action pi of S. So we don't get to choose, we don't get to maximize over it. So that's just gone. After we committed to pi of S, we land in a chance node. In that chance node, an averaging will happen over next states, and they'll get weighted by the probability that you land in that particular next state. What do you average? Well, you average is what you would get for landing in that state. What do you get? Well, you get something for the immediate transition. That's the reward. And you will get things in the future from that when you state S prime onwards. So that's captured by V pi S prime. It's defining V pi recursively as a function of itself, right? Because again, if there's 100 states, you'll have 100 of these equations, and your V pi for state 1 will be defined in terms of the V pi's for other states, and for these other states will be again defined in terms of V pi of this first state. So it's a recursive definition. We'll need to get out of that. We'll get out of it the same way we got out of it for value iteration, but that's the same equation as for value iteration. This is the Bellman equation for a fixed policy. Okay, so let's look at an example. Here we have a first policy, always go east. Not great. But when you just see the table that maps from states to actions, you don't know that. Like the only reason we know that that's not great is because we have this bird's eye view and we see the fire pits and so forth. But the computer doesn't look at things that way, right? You just get a table, you get a transition model, you get a reward function, and you got to compute something still. The computer cannot eyeball this and say, oh, that's a bad policy. You have to compute something. And then here's another one. Always go north. It's probably the right thing to do. But again, computer doesn't know that from just looking at this table. This policy over here, just looking at that doesn't say enough to say that this is the right thing. You need to evaluate this numerically. So let's assume we did that. We ran something that finds us the values for each of these two policies, and we'll see soon how to do that. And here are the results. Let's see if this makes sense. This is the always go right policy over here. What's happening over here? Those are exit states. You have no choice. The policy will always exit, and you get a reward of -10. Same over here. So those are all meaningful. If you end up over here, you get the reward of +100. Again, that's very meaningful. Now, the interesting ones, though, are the three over here. What are those saying? Well, here, well, not very good. -8.69. What is that encoding? Well, usually when you make that right action, you'll land in the fire pit on the right. You'll get a -10 at the next time. The -10 at the next time will be discounted, so it'll count for a little less than -10, but it's still going to count for something pretty bad. Same thing over here. Same, but it's a little less. Why is this a little less? Well, what happens is if you somehow don't succeed at going right, and end up going up instead, just by random chance, that 10% chance you have to be not following your action, then, well, you'd be over here. And same thing would happen over here. 10% chance you move there, 10% chance down. And so in the off chance that your action doesn't execute the way you anticipate it would, you might end up somehow making it to this top state where things are good. And so the closer you start to that top state, the better the value of this policy is, because the better the chance that you get lucky and still get there. How about over here? Here's the other way around. Hold on. It's not the other way around. It's very similar. Here we have something very similar. It's still 100 up here and -10 on the sides. But now let's start from close to here. What's happening close to there? If you start here, you get usually a success. You move up 80% of the time. So 0.8, you'll move up. Then at the next time, you'll get the 100, but that will be discounted. Let's say that's discounted by 0.9. You only have 0.8 times 0.9, which is 0.72, times 100, which is 72. This is a lower number, so it looks like the discounting is even higher than that in this example. Down. So, of course, possible you get unlucky, you move off to the side. Actually, let me recap that. If you were to move up, and you have an 80% chance of doing that, you have 0.8 times, then discount gamma times 100 at the next time. But then also you have 0.1 times if there's no living reward, there's no current reward, just the value at the next time, you have then gamma times the value of this next state, which could be the -10 state on the right, or the -10 state on the left. So for no living reward, this is how you would end up with the value of 70.20. 3 possible outcomes, you average. Here it's worse because, well, more chance of failing along the way and so forth. So that's what the values of these two policies look like. Now you can compare the numbers. You can say the policy on the right is better than the policy on the left because the values are better in every possible state. Okay, how do we compute these? Very similar to what we did to find V star. In fact, you can think of this as a very special case, right? You can think of us as having redefined a new MDP in which there are fewer actions. In every state, there's only one action available, and we're just computing the optimal value in that new MDP, where the policy has already been fixed for us. It's the same thing as fixing a policy is to reduce the actions in your MDP. So you return to the recursive updates the same way we did before. Initialize at 0 with all zeros. This again, this is a vector with an entry for every state. When 0 time steps are left, you'll get 0 because there is nothing to be earned. There's nothing happening. Then you recurse. You go from k to k plus 1 by saying, well, first you take an action. You don't get to choose that, so there is no max. Then you average over the outcomes. That's this averaging over here. And what do you average? Well, the reward you get. There's an immediate reward over here. There is a future sum of discounted rewards there. And the future stuff gets discounted by a factor gamma. If you run this in practice, you'll notice that you'll have a double loop here. You will loop over all, you'll say outer loop over k. K starts at 0, then k is 1, then k is 2, k is 3, and so forth. And you'll have an other loop inside that loops over all states S. Because you have to do this update for every state. How efficient is this? Well, one iteration is order S squared because you have to consider all pairs of states in one update over here. Hold on, let me rephrase that. You have to consider all states S prime over here. You do this for all states S, so you have order S squared. Without the maxes, this is actually just a linear system. So there's an alternative way of solving this. We saw in value iteration that we could solve this, go for this iterative procedure. It will converge to V star. This here, the same thing. It will converge to V pi. But the equation satisfied by V star was this nonlinear equation with maxes in it. The equation satisfied by V pi is the equation we saw over here. What are the variables? The variables are the variable V pi s. So if there's 100 states, you have a 100-dimensional vector V pi, and those are your 100 variables. Your transition model is known. That's just a 3-dimensional table of numbers that you're given when you're given the MDP. Your reward function is known. It's a 3-dimensional table you're given when you're given your MDP. So the only unknowns are the V pi's. How do they appear in this equation? Linearly, right? It's just, here there's not even a coefficient in front of it. And then here this one appears with a coefficient, the weighting here by the transition model, and then a weighting by gamma. And then gets summed with other terms that are similar. So this is actually a linear set of equations. So in principle, to find the value of a policy, pi, instead of doing this iterative procedure, an alternative method is to say this is just a linear system of equations. Linear systems of equations are very straightforward to solve. It's just a matter of matrix inversion. In fact, you can even do it slightly more efficiently. So you just ask your linear equation solver, hey, give me the solution, and there it is. So we now know 2 ways of doing policy evaluation. One way is the way we've seen for value iteration, is this iterative procedure over here. Another way is to just solve a linear system with as many equations as unknowns, and the number of equations and unknowns is equal to the number of states. Any questions about the evaluation? Yes?
I'm still kind of bad at what the T and R and X, pi, all the different terms. Are they on one of the slides that you explained them? And I could go and look at it again.
Actually, let's do the following. Let's quickly backtrack to the very first slide. These are the terms, and they're coming back on almost every slide this lecture, next lecture, and the lecture after. So what were those terms? Let's erase all ink on slide and get a pen back. T is the transition model. T, S, A, S prime is the probability that if you started in state S, took action A, that you would land in state S prime. So is the probability sitting on these transitions over here in your expected max tree. The rewards are the numbers associated with the transition itself. So for this transition here, there will be a reward. That transition encodes that you started in state S, took action A, and then by chance transitioned into state S prime, and there will be a reward for that particular transition. So those are the things that are given to you. Other things are things that we compute ourselves. Sure. Any other questions? Yes? Okay, the question here is we've seen two things now. We've seen value iteration and finding optimal values V star and Q star. And we've seen another idea, which is evaluating policies. What's the relationship? Right? Yeah. Oh, for these two, you want to compare this one with this one? Okay, for these two, the difference is it's a choice, implementation choice. If you have a really good linear equation solver available to you, you can use it to do policy evaluation. If you don't have that available to you, you could write this thing yourself here, and this recursion, this will converge for you to the solution, the values V pi. Now, why would you do one rather than the other? It really depends. Like, when is this fast? This tends to be fast when your gamma is really small, because things converge very quickly for a small gamma. If your gamma is very close to 1, the time it takes for this to converge can be pretty slow, and just solving a linear system of equations can be faster than working through those iterations till you're converged. Now, something we'll see towards the end of this lecture is that once we're a little further along, you'll see that we have value iteration, and we'll have this other thing called policy iteration. And it turns out you can interpolate between them. And if you want to interpolate between them, you'll have to use this version. This is a little bit of anticipation. It's not clear yet now, but this is why we want both of these ideas. If you want to literally execute this and gamma is relatively high, you probably always want to go with this. But to get the intuition of what could be done, and then later interpolate between these two extreme approaches, you want to understand this part. Sure. Any other questions? Yes? Yes, in practice what you would do is, if you do these iterative updates for V pi or for V star, you would check, you would have a new vector. Essentially we keep track of two vectors. You have your first vector, which is your current, let's say your VK, and you'll call that your V old. You don't need to keep track of one for every K. You can have your V old, and then you have your V new. Your V new is what will be sitting on this side. And your V old is what sits on this side over here. And they'll be there for every state, right? This is both for V pi and for V star, whatever you want to compute. You'll have these two vectors. You'll go from old to new with this update. Then what you'll do is you'll check, how different is my V old from my V new? If they're almost the same, then I'll call it done. If they're still quite different, then I go back, I push my V new into my V old, because I don't need the old V old anymore, and then I do this again. That's the way it implemented. And then there are guarantees that you can get. They're not on the slides here, but there are guarantees of the type. If, the guarantee of the type will be something that says, if V, let's write it this way. If the max over all S, V old S minus V new S, we take the absolute value because we care about the absolute difference, not whether they're bigger or smaller, is smaller than epsilon, where epsilon is some small tolerance you pick. Then there are guarantees of the type. If that's true, then you have that the max over S of, now it depends whether you work with pi or V star, but let's say V star. Let's say this is true. We're running the value iteration version. Then you know that V new S minus V star S, the max over all of them is smaller than 2 epsilon over 1 minus gamma. I'm going to put this in quotes because it could be that I'm off by a constant factor here, but this is what it looks like. This is the type of expression you get and the type of guarantee you get. And what's interesting about it, as is to be expected, is that, of course, the closer your discount factor is to 1, the more you could still accumulate that you haven't accounted for, and so the worse this bound will be. For very small gammas close to 0, you will very quickly get a very good guarantee. And you can even get guarantees beyond this. You can then even say, if I were to use this current policy for what I have, then I also have a guarantee that I'm very close to doing as well as the optimal policy. In practice, you can often just set this to machine tolerance, essentially. You just run it till machine tolerance, and it'll be pretty fast for relatively small state spaces, and you're done. Any other questions? There's another question somewhere in the back before. Resolved? Okay. What we'll do now is something called, we said, let's look at policy methods. Where we look at a policy, we've seen how to evaluate it. Let's now take a look at how we can extract a policy. So we assume we're given values now. We went from policy to values. Now we're going to go from values to policy. So let's imagine we have the optimal values V star available to us for every state, and they're shown on this grid here. Don't look at the arrows for now. Just look at the values, right? And just think about what would be the right thing to do from this state over here. Well, looking just at the values, the state up here looks pretty good. 0.98. So you might say, well, the right thing would be to move up. It's actually not that easy to read it off. In fact, we look at what was computed by running value iteration and finding the optimal policy. It's actually saying that you should go this way. Why is that? Well, we know that this is a tricky situation where if you keep trying to bump into the wall, you'll definitely never go into the fire pit. And then sometimes you get lucky and you scoot off to the left or the right, and then you can do something better. But what this shows is that you can't just look at these values and basically not say, oh, move in the direction of the highest value. That's not doing the right thing. Because you need to account for the probabilities of the transition probabilities. You need to do essentially a one-step look ahead with expectimax. That's what you need to do to find the right action. So, not obvious, but we do a one-step look ahead with expectimax. What does that look like? Looks like this. Let's break it down. Again, expectimax, remember we have a maximizer, some actions available to us, then there are chance nodes and stochastic transitions there. So what's happening? First thing you do in your state S, you get to choose among actions, and we want to pick the best one. So that's the max overall actions here. After you pick an action, what happens is, well, what you're going to get is a weighted sum of rewards, weighted by the probability of going to each possible next state. And what are you summing together? Well, the reward you get for the specific transition, and then what you'll get in the future. What you get in the future on expectation, and it's discounted. So what is this equation saying? It's just saying set up a small expectimax tree where the utilities at the bottom for the chance nodes are given by your V star. That's your function at the bottom is V star. And in that small expectimax tree with just two steps, a maximizer layer, a chance layer, in that small tree, you compute the value of that node, and in particular, you look for the action that's the right action to take in that small tree, and that's the way you choose your optimal action. Why is that true? Well, we know that's true because we know to act optimally, if we do the optimal thing right now, and optimal from then onwards, we're doing the right thing. What we're looking at here is, for all of them, we evaluate the optimal thing from then onwards. We're accounting for that in when we evaluate a particular node. So you can do just a depth 1 or depth 2, depending how you count expectimax search to find the optimal action. And in math, and that's what we will be working with throughout this and the next 2 lectures, instead of specifically every time drawing that tree, we'll just write this equation over here. And that equation encodes policy extraction and is encoding just what you're already doing for your project 2 for 1 ply. But keep in mind, the important thing is that we put V star in the bottom layer here, right? That's what makes it work. correctly accounting for what will come in the future. Okay, so that's policy extraction from V star. We find the optimal policy if somebody gives you V star this way. How about if you know the Q values? These are the Q star values. What is the optimal action? For example, let's say over here, what's the optimal action? Well, we have 4 values there. 0.9 is the highest one. That corresponds to going west. That's all you need to do. Your Q values have stored for each action. If you were to take an action and then be optimal from then onwards, this is what you're going to get. You just look it up. There you are. West is the right thing to do. You can do that for each one of those. You can look over here. What's the right thing over here? 0.89 is the highest, so this is the right action to take here. So if you were to code up value iteration, you kind of have 2 choices here. You code up value iteration, which you know how to do. You find optimal value function, V star. You know in the inner loop of running value iteration, you're really computing your Q stars anyway, because you're always doing this 1-ply expect to max thing to do the updates. Either you could just keep track of those Q stars and store them. And then when you're asked to act, you just look up in your Q star table what the right action is. Or if you only stored V star, then you have to do this little bit of work to extract the optimal action when you're asked to act in a particular state. Yet another thing you could do is, while you're running value iteration, just also store the policy that you found while you're running it. So you have 3 options, really, on how you would kind of store things when you're done with value iteration. Okay, so Q values are easy to work with. This will come back in next week's Tuesday lecture, where we'll see we really need Q values in some of our algorithms when we're doing not just planning, but actually learning. Okay. Now we'll put this together in something called policy iteration. We've seen how to go from a policy to a value, from a value to a policy. Now let's do something that combines both. So this was value iteration, and the reason we're going to do this is because it might be better than what we've seen so far for certain problems. So value iteration did this. Why could this be expensive? Well, let's think about what's happening. You have a loop here. For all k from 0 through infinity. Then inside for all k, so you have a for all k, you do this. K equals 0. Actually, you initialize with 0. So equal 1. No, 0 actually, the way it's set up. This k is here. So 0, 1, 2, and so forth, till somehow you reach the right precision. Then this thing here is happening for all s. Then for all s is looking at all actions. And then it's happening to be looking at each state as prime. So again, for all states. So the complexity of this is order number of states squared times number of actions. This can be a lot of work. So that's what you do in one iteration, and you do it multiple times. An interesting observation people have made is that from iteration to iteration, it's actually rare that the best action changes. Think about it. In a given state, when you have k time steps left or k plus 1 time steps left, often the right thing to do is the same. Not always. It can be different when you have 1 time step left or 2 time steps left what the right thing is to do for a certain state. But very often, the amount of time left will not influence what the right action is, or not for every change in time left. So one thing you could argue then is that, well, we're always doing this max, always doing this for all actions here, having this action factor here. If you have a lot of actions available in a real type situation, or maybe if you have a continuous action space, you do a lot of work for no good reason. And another thing people have observed is that often, even though your values are still changing, the policy is already fixed. So you haven't correctly computed the value for these states, but whether you act for 1,000 time steps or 1,000,000 time steps, it might be that the action to take in each state is going to be the same. And this thing value iteration doesn't really account for that. Let's take a look at that. Here is when there is 0 time steps left, Gridworld. Now let's look at the values. 0 times left, 1 time steps left. What do we see here? A 1 and a -1 in the exit states, and a -0.1 corresponding to the living reward. 2 steps left, you see this kind of values propagating, and these values are changing, and after 100 more or less, this is converged. Now let's look at this again. Instead of looking at the values, look at the actions and what they are for each state. So you could focus in on 2 or 3 of these states and see what happens. How often do they change? Not that often. If you look at what happens here, some actions are changing, some actions are changing, some changed again, and from here onwards, after iteration 4, no actions change anymore, only values. So that means after 4 iterations, we were actually done. But value iteration doesn't know it. Value iteration only realizes we're done after 100 iterations. Questions here?
I think it's true for pretty uniform like space. If you have something like very big and you get a lot of weird stuff happening very far apart, then things can change pretty often.
So the observation here is that it really depends on the MDP how often your actions will change, right? If you have rewards that could be very positive or very negative that are in different directions at different distances, then every time you're able to reach a new type of reward, your actions might completely change because now you decide, oh, given I have this much time left, I should actually go for this further away reward because it's bigger and now I can reach it. And that's absolutely true. So it depends a lot on the MDP how exactly this will play out. But it is the case that even though we are converged, value iteration doesn't know it. And so ideally we detect that we are done finding the policy, and the algorithm we'll see as an alternative is able to detect this. And so when it takes a long time, sure, it'll say it's not done yet. But if it's a short time, then it'll know that it's done more quickly. So the key observation here is that these actions don't change a whole lot. And after 4 iterations, they don't change anymore at all. So here's an alternative approach to compute the optimal values. It's called policy iteration. What you do is in step 1, you do evaluation. What does that mean? Somebody gives you a policy. You just go ahead and evaluate it. We know how to do that. There's many ways of doing it. But you just pick one of the ways. And then you improve. What does it mean to improve? It means you do a policy extraction step. You've found the value for each of the states under your current policy. Relative to those values, you now run this depth 1 expected max search for each state and find the optimal action relative to that set of values. Okay, if you do that, and you do this until things converge, you'll also find the optimal values. And you will find the optimal policy. And the nice thing is that if in this process your policy doesn't change in 1 iteration, it'll never change again. So you right away know when your policy didn't change that you're done. And sometimes this is done in a very small number of iterations. Okay, so let's look at this in a little more detail. What does evaluation mean? This could mean this thing over here, which is a lot like value iteration, but we don't have the max over actions. And improvement, that's the 1-step look ahead. That's this equation over here. Remember, this is your expected max 3, where the utilities at the bottom here are your V pi's that you had from your evaluation. So now you keep track of 2 things. There's a policy you keep track of and a value, the value for that policy. And you keep updating one at a time. Here you update the values. Here you update the policy pi. It's a different approach. One way to think of this is that you're actually running value iteration, but in a slightly modified way. How is that? What we do in value iteration? Value iteration would essentially do this, right? Find the optimal action, and then also update the value accordingly, according to this specific equation. The optimal action is the argmax, the optimal value is the max, right? What we do now is we do find that action, and then we say we found the optimal action for our current values for each state. Let's stick with it for a while. We know they don't change very frequently, and let's run some updates to our value function over here where we don't bother changing the action. And then at some point, we go back to being also willing to consider all actions again and updating the action. Value iteration is one extreme. In every update, you update both value and action. Policy iteration is the other extreme. You keep updating values until you have the value of that policy, and once that's converged, you move to updating the actions. And then you go back to values. But you can do anything in between, and often the most efficient algorithms are somewhere in between, where you do a couple of updates where you keep the action fixed, and a couple of updates, and then you do an update to the action, and you interleave that. And it turns out all these variants happen to actually work as long as you update everything infinitely often. Yes? Say it again? Okay, you need to initialize. So the initialization is not shown here. You initialize with some policy. It could be anything. You could just initialize with a policy that's always north, for example, or always south, whatever action space is available to you. Then you evaluate that policy, you improve, and keep going. You could start also with a value. You could say, I'm starting with a value all zeros, right? And then you could, relative to that value, pick a policy, which means you would start in the second step, and then go back to the first step. Either way is fine. In policy iteration, you do the switch when this has converged. That's when you switch. In things that interpolate between value iteration and policy iteration, you cannot arbitrarily switch around. The extremes are value iteration and policy iteration, and the others are just things that switch whenever. Yes? That's a great observation. So the observation here is, if you were converged to the optimal policy, what will happen? Let's say you have the optimal policy, you do your evaluation here, you find the optimal value, because the optimal policy has the optimal value, V star. Then you go down here, and you would have V star there, because you had the optimal policy. You'll have V star as the value of that optimal policy, right? And then when you update your policy, you'll see that it doesn't update. You get pi star again, and that's when you're done. That's exactly when things will stop. What's the comparison? We discussed most of this already, but the difference is in value iteration, the main thing is every time you do an update to a state, you do the max over all actions, and then the weighted sum over next states, right? And you don't have to track the policy because it doesn't really play a role. You just keep track of the values. Policy iteration, you do many passes where you fix the actions to your current policy, and once it has converged, then you switch to an action improvement for each state. Keep in mind that your policy evaluation doesn't have to be this iterative process. In your policy evaluation, over here, instead of running this till convergence, you could also solve that linear system of equations. Equally good. That just as well finds the value of the policy. You have two options here. We had idea 1 and idea 2. Both are valid for policy iteration. But if you want to do something intermediate between value iteration and policy iteration, you need to use that idea 1, where you actually run this, but you don't run it till convergence. Okay. In summary, so we're looking at MDP algorithms. You want to compute several things. You want to compute optimal values, use value iteration or policy iteration. Both will work. Compute values for a particular policy, that's policy evaluation, and turn your values into a policy, that's policy extraction. It's one step look ahead. Those are the algorithms we've seen. They all look the same. They all kind of do one layer of expected max. Sometimes the policy is fixed, sometimes not. But they essentially do the same thing. They look very much the same. That's good. That's the right impression you got. But it's also important to understand the subtle difference and see why the max is there and why it's not there in other places. What we're going to do now, let's take actually a 2-minute break. What we're going to do now is we're going to switch from planning to learning. Okay, let's start with the last little part here of today's lecture. Let's look at bandits. So, why are we looking at bandits? Bandits are kind of the common example people use in reinforcement learning. And reinforcement learning is what is next on our agenda. It's kind of the canonical, kind of fun example to look at. And the idea there is kind of, you go into a casino and maybe some of these bandits, these slot machines, will have a better payout than others. And you kind of want to figure out what you should do in that kind of casino. That exposes a lot of the challenges in reinforcement learning. And so we're going to give a little sneak peek at what it is really that we're going to care about in reinforcement learning. So you're faced with two bandits here. One bandit always gives you 1, guaranteed. You pull that lever, you get $1. Okay? The other one, you pull the lever, it could give you $2, it could give you 0. You don't know what it's going to be, it's stochastic. Let's model this as an MDP. So what are the states here? There's a W and an L state. W means you just won. L means you just lost. Let's look at one of these states. Let's say you just won. After you just won, you could take one of two actions. You could pull the red or the blue bandits lever. If you pull the blue bandit, you have a guarantee that you win $1. So that's your transition shown from the state W. You go back into W, and the reward associated with that transition is $1. If you pull the red lever, then what happens is, well, 75% chance you actually win. That's pretty good. You get $2, 75% chance. 25% chance you don't win. And you go to the state where you just lost. If you just lost, the same transition model holds true in that you still have a 100% chance of winning by pulling the blue one, and 75% chance by pulling the red one, 25% chance that you lose when pulling the red one. What we'll look at is this particular MDP. We assume no discount. We assume there are 100 time steps, just to allow us to do some computation out of the top of our head without having to implement value iteration and then see what the numbers are. We make a couple of simplifying assumptions there and how we specify things. No discount, 100 time steps, and it should be clear to you that both states have the same value. What is the value? Value is expected sum of rewards going forward. It doesn't matter where you started. It doesn't affect your future here. It's a very special MDP. It doesn't matter whether you just won or lost. What you're going to get in the future is the same, because you can either case pull red or blue, and the probability of winning and transitioning into win or loss is the same independent of where you started. So we know that the value of both states is going to be the same. We start asking ourselves the question, of course, what is the value of each of this state? All right? Any guesses what the value might be? Well, there are two possibilities. You could play red, you could play blue. Just the way this is set up, the optimal policy will either to be always playing red or always play blue, right? One of the things is the right thing to do, because you always kind of land in the same situation. What happens if you always play blue? 100. So always blue, you get 100. On expectation, but in fact, it's a distribution that has probability 1 of being exactly 100. It's a very special distribution. It's a deterministic distribution. What if you always play red? What's your expected value then? So I hear 150. Does that mean you're getting 150? No, it's a distribution over outcomes when you always play red. You can end up with 200 if you're lucky 100 times in a row. You can end up with 0 if you're unlucky 100 times in a row. But on the average, if you were to do it as many times, it would average out to having 150 over many runs of this game. Okay, so what's the right thing to do then? If you want to optimize your expected utility, the right thing to do is to always play red. So what did we do here? We looked at an MDP, which is what we've been doing all along in the past 2 lectures and even in previous lectures in expected max form. We computed the value for different policies. There were 2 policies for which we computed the value. There are only 2 meaningful policies here. And we said, well, the optimal one is to always play red, and we're done. What happens now? We did all our computation. We go into the casino. We know what to do. What do? We computed the optimal thing. We go in and we say, boom, play red. We got 2, play red again, red again, red again. We keep doing this, and we happen to get some payout. That's offline planning and then playing. Now let's switch things around. And this is what we're going to look at going forward, online planning. What's different? What's different is that now there are these question marks here. Where are they sitting? They are sitting for the red slot machine. It's saying you don't know the probability of winning or not winning. It's unknown to you when you start. So you're not given the transition model. You don't know the transition model. There's just question marks there. It's a different setting. What should you be doing now that you don't know what those numbers are? You can't run value iteration, you can't run policy iteration to find the optimal policy because you don't have the numbers to compute it. So the right thing could be to say, well, let's just play. And when we play, maybe along the way we'll learn how likely it is that we win. We know ahead of time that for blue we always win $1, but red is sometimes 2, sometimes 0. So the right thing to do could be to say, well, let's just play red, see what happens. If we play sufficiently many times, we'll get a feel for how often it pays out. Yes?
We assume that the previous action, the next thing is going to be independent of what we did.
Yeah, so we make some assumptions. So all the assumptions are shown here. These are all the assumptions. We have an MDP of the same format as we had before. We just don't know some entries in the transition model. That's the only thing we don't know. So you could say, well, how do we find out? Pull that red lever, see what happens. If you pull that often enough, you can see on the average how often it pays out, right? And then once you know that, you can start planning, right? So what do? You pull red, red, 0, 0 again, 2, 0, 2, 0, 0, 0, 0. Maybe at this point you say, well, I've done this 10 times. With the blue, I would have gotten 10 for sure. With red, I'm ending up with $4. Doesn't look like this red one is paying out all that often. Maybe I'm done with my kind of trying out the red one. You switch to blue and start just exploiting your knowledge that red isn't that great and start playing blue consistently. But maybe not, right? Maybe you say, well, maybe this was an unlucky streak. Maybe red does pay out typically. I just got really unlucky and I should pull red a little longer, see what happens. It's a complicated question. It's hard to decide what to do here. You don't know what the right thing is. So what just happened here? This wasn't planning anymore. This was learning. So when we're still acting in an MDP, but we don't know some of the parameters of the MDP, that's called reinforcement learning. So now we need to act. And while you act, you learn about the system, and then maybe based on that, you can plan. But you get a lot of new challenges here. And this example illustrates, in some sense, all the challenges that there are for us in reinforcement learning. The first challenge is exploration. You have to try things out that you haven't seen before. Because if you don't try them out, you don't know how good or bad they might be. So there's something there, some tension there, that you want to try things out. At the same time, if you know some things are good, you want to exploit that and take advantage of that knowledge and collect your rewards from there. Keep in mind, you only get to act a finite amount of time, or it's discounted, so you can't just wait forever to exploit. You need to start doing it at some point. So there's a tension there. Should you explore more? Should you start exploiting? That's something we'll need to resolve. Then there's something called regret. It's a thing where you say, if you got to play only 10 times, you end up with $4, and you could have gotten 10, you feel regret. You say, I knew I could have gotten 10 for sure, and now I ended up with 4. That's regret. Does that mean you did the wrong thing? No, it actually doesn't mean you necessarily did the wrong thing. You started with a lot of uncertainty. You couldn't know what would happen. And now, maybe exploration is the right thing to do. You just got unlucky. In your world where you are in, exploration ended up leading to nothing good. But if you had been in another world, maybe that exploration would have led to something good. So you can't ahead of time say exploration is right or wrong. You'll only find out as you go along. But no matter what, whenever you explore, it's likely to end up with regret. So that's something to keep in mind. Then there's this concept of sampling. Just taking an action in a state doesn't tell you what will happen for that state. Transitions are stochastic. You'll have to see a state-action pair multiple times to get an idea of what is the distribution over possible outcomes here. So you need to somehow know how to learn a distribution, estimate what that distribution is. So overall, MDPs are great the way we've looked at them so far, and we can plan in them. We know how to do that now. But in the real world, usually there's nobody who ahead of time can tell you what the transition model is, what the reward function is, and you will have to learn as you go along acting in the MDP. And so we'll face all of these challenges in the next 2 lectures, and that is called reinforcement learning. See you on Thursday. Sure.
The Gridworld.